It's now possible to describe the full dynamics of the system. The whole predator-prey interaction is described by a pair of differential equations. We have the dynamics of the stock of resources S, which is actually the prey, and the stock of population, which is L. So as we have seen, the stock of resources increases with the natural growth, which is this part, R times 1 minus St over K, minus the harvest, which is alpha beta LT, and then harvest, of course, is a function of the population on the island. The population growth of the island is a function of births B minus deaths D, plus phi alpha beta st, which is an increasing function of how much food is available per person, which of course multiplies LT. The easiest point to start is always to start with a description of the steady state, which will be actually pairs of S and L, which will be then thus S star and L star, at which both the population and the stock of nature do not change. You may be surprised to learn that we have actually not 2, not 4, but 3 steady states for the whole system. I have listed them here, but now your job is to guess from the name what they mean, or more precisely, what may be the values of S star, L star, and L star for each of them. So the 3 of them are the unoccupied island or virgin island, the collapsed island, or the sustained island. So think about it for a while. All right, so if you think in your head of virgin island or unoccupied island, what should you have in your head? Well, probably an island with that its nature fully intact, but nobody on it. So that's obviously a case in which the stock of nature S star is at its carrying capacity K, but nobody has yet arrived on the island, so L star equals 0. A slightly less happy state is the collapsed island, which will be referred to a state in which nature stock is actually equal to 0. And since the nature stock is 0, then population stock is also 0. So it infers to a state in which nature has been overly exploited and has collapsed, and as a result, the population of the island has completely collapsed as well. And then the third one, of course, sustained island means that it's able to sustain both a positive amount of resources and a positive population. So both S star and L star are larger than 0. To find the sustained island, we must use the equations for the sustained island for each dynamics. So that's why I named them sustained island. From the population dynamics, we have found that the population does not grow when S star equals to D minus B divided by phi alpha beta. So from the fact that the population must be stable, we find an exact solution for S star. And then from the resource dynamics, we have found that resources are stable when S star equals to K minus K times alpha beta divided by R times L star. So that gives us an easy two variable and two equation system that we can solve easily by just say substituting S star in the second equation. And then if we do that, we can then just go ahead and isolate L star. And after computing, we can find that L star equals to R divided by alpha beta, which multiplies 1 minus D minus B divided by K phi alpha beta. So this looks like it answers the age-old question, is it possible for human and nature to live in peace? Well, according to this model, yes, as long as actually the resource stock is exactly equal to d minus b divided by phi alpha beta, and the population is exactly equal to r divided by alpha beta times 1 minus d minus b divided by k phi alpha beta. So that last equation has interesting interpretations. We see that increasing the reproduction rate of nature R and the carrying capacity both allow the island to sustain a larger population of islanders. However, the interesting part is that what can we say about beta, the taste for food? Think about it for a while. What has the taste for food as a consequence for L star? Well, we see that it plays the same role as farming efficiency, and it is actually ambiguous because you see it's at the denominator, but with a plus sign and a minus sign in front of the fraction. So the interpretation is not so straightforward, but it makes sense if you think about it. So if people don't care about food, they don't like eating, well, if we go back to our dynamics of population growth, then it means that they're not going to extract a lot of food, and population is not going to grow too much. But if they really like food, they like eating a lot, and they want to spend a lot of time on it, well, what's going to happen? Well, they start to overexploit nature, and actually the steady state stock of nature is going to be very low, and as a consequence, the steady state population is going to be very low as well. So it looks like in that situation, we could imagine that statue building, maybe it's a waste of time, or I don't know, it's art, but actually it's actually better for them to spend less time harvesting and spend more energy building statues to actually leave nature regrow by itself. So that's the description of all our steady states. Now to understand a bit more what happens outside of the steady states and how we can converge maybe to one or the other steady state. So we have to go back to our phase diagram. It's now time to look at the whole dynamic of the system and be able to describe what happens outside of the steady state. So let's start with what we've learned about the resource stock. So these are all the values of S and L at which the resource stock doesn't move. So S dot equals 0 or ds dt equals 0. And what we have just seen is if we want to know what are the real steady states of the whole system, we have to ask ourselves not just when S is not moving, but when L is not moving as well. So we have to basically add up the second part of it. Here it is. So these were all the values at which L is not moving. So L is at steady state. And of course, for the whole system to be at steady state, then we know that we have to have both L and S at steady state. So where are these values? Where, as you may guess, they are the point at which both are crossing each other. So both there are points that are common to both of them. So it looks like we have 3. So it looks like it's good according to our description of earlier. Now you may think in your head and try to figure out where the 3 steady states are, what the names are. So I'm not going to tell you right away, just think for a while. All right, here they are. Right, that was hopefully not too difficult. So why are we at the Virgin Island here? Well, because the resource stock is at value K, so it's at full carrying capacity, and the population is at 0. So here the resource stock cannot change because it cannot increase further. The island is full of nature and there's no way to have more. And there's nobody in the island, so no way for the population to increase. Slightly less positive steady state is the collapsed island, where essentially people have cut down all the trees and have all died at the same time as a consequence. So basically we have no nature and nobody in the island. So it's a very depressing state, but it's a possible steady state of the model. And finally, the more positive steady state is the sustained island, in which it is possible to maintain a positive stock of nature and a positive value for L. So we already know that the stock of nature is d minus b divided by phi alpha beta, and we have already computed the value of S at that point. So these are all the steady states. Now, of course, the more interesting part is to look at what happens away from the steady state. We have already done that, and we have done it separately for the dynamics of the resources and dynamic of the population. But same way, we're going to put back everything together. So when you look at this, the thing you have to do is to do it systematically and do it step by step. So don't rush it. So let's start again with the resource stock. And what we have learned is, for instance, if I am at this value of the steady state, for instance, for the resource stock, and I increase the population on the island, what happens to the dynamic of S? Well, if I increase the number of islanders, harvesting goes up and S should start to decrease. So we have learned that everything above and to the right of this line has to be a point where S is decreasing, so S dot is negative. So what we did is draw a downward arrow, so this arrow is still valid. And same thing if we decrease the population instead of increasing, or if we decrease the stock, same thing, then the stock is going to naturally start increasing until it reaches its new steady state here. So we can draw these arrows there. We have now 4 quadrants, but in terms of the resource stock, it's the same story. I have one dynamic on that side, one dynamic on that side. Now, of course, that's just half of the story. The other half is to ask what happens to the dynamic of the population. So what did we learn so far? Well, we've learned that, first of all, it's just described by this value of S. So we know that if the nature stock is d minus b divided by phi alpha beta, L is at steady state. And imagine that from that value, I slightly increase the stock of nature. Then what happens? Then obviously people are going to be able to harvest more and sustain more kids, and then the population is going to grow. So it means that L dot is going to be positive, and the dynamic of the system will go that way to the right. And the same thing, but in reverse. If I start at steady state, let's say here, and I decrease the amount of resource available, then people are going to not be able to cultivate as much, and they're going to start to starve. So L is going to start decreasing, and L dot is going to be negative. So we can also add that on our graph. So that's how you draw these set of lines. So they describe essentially the whole dynamic of the system. And now we can really be sure that we know where we're going, because we know where L and where S are going, the two state variables of our system. And as you can see, it looks like we're maybe drawing circles around the steady state of the sustained island, because we're going in this direction, then in that direction, then in that direction, then in that direction. So here we're not saying so far where this is going long term. We don't know if it's going to diverge or converge or go to a collapsed island or go back to a virgin island. For that, we have to have more information. But it's still possible to describe it this way, to have a certain idea of what's going on. Last thing we can ask, just to see if you really understand what's going on. So as we can see, we're going in this direction, so to the left and up here, and here we're going up and to the right. So my question is, for instance, at the point where we exactly cross the sustained island case steady state for the resources S, what is going to be the arrow? Is it going to be this way or that way or that way? Think about it for a while. So maybe I should ask again. So here I see that if I make, these are two vectors, but of course the direction of the system is the sum of these two vectors. So the sum would be a vector that goes this way. And here the sum would be a vector that goes that way. And the question is, in what way would go the vector that crosses exactly this blue line for the sustained island for the resource stock? Well, it will be perfectly vertical. How do I know that? Well, because when the resources are here and the population is just here, for instance, then I know that that here I'm at steady state for L. Being at steady state for L means that L doesn't change. So it means that in the neighborhood of this point, L is constant. So basically I'm going to cross, and when I cross this line, I'm going to cross it exactly vertically. And now, okay, so that was the first try. Now ask yourselves, at what angle do I cross this steady state for S line? So the sustained island for S, is it going to be this way, that way, or that way? Think about it. Well, if I was to put an arrow that goes exactly through this line, it would be perfectly horizontal. Why? Well, because I know that in the steady state for S, then S doesn't change. So if I'm here, then ds dt is 0. So essentially, while I'm passing through this line, then I know that S is not going to change. So I'm going to cross the line exactly horizontally. So that's all we can say about the dynamic of the whole system right now. And the last thing we have to do is to ask what's happening in the long term and what may have happened on Easter Island in the end. But before that, we're just going to have a small quiz to see if you can put some pieces of the puzzle together.